I go to the next one, ask him to stand up, then you know who is on question, okay?
Okay.
Because it's always the same guys who ask the questions.
Really?
Very long, very out of your presentation.
Out of the presentation?
Sometimes it happens, so I know these people, and I can avoid that. Okay, that's one thing.
Okay.
At the end, we make an appointment for an interview for the magazine.
Okay.
That's all right.
Yeah, for sure.
Okay? Good luck.
Thank you. It's good to be here.
Will that bother you in that pocket?
No, it's good.
Okay.
Yeah.
Cool. Thanks.
Thanks.
So it's 4:3. Screen is. It's a 4:3 aspect ratio. So.
Which is what, different than this?
You're at 16:9. So I just wanted to see.
Okay.
Can you just go into a slideshow mode? All right.
It looks
gonna work
fine.
out.
Yeah,
Great.
it looks fine. What's up?
Jason
Hey,
Corbelli.
Jason. Good to see you. Yeah.
Nice to meet you.
It's charged 78%.
Everybody getting settled. Welcome to day 3 of our conference. Now, the Global Breakthrough Energy Movement is very proud to introduce to you Mr. Jamie Janover.
All right. Can you guys hear me okay? Just want to make sure all the technical stuff is. So should I start? We're 10 minutes before 10. Is that good to start now? Wait for a memory card. See, I knew. I know how these things work. We think that we're so technologically advanced, which we are in some ways, but we're also in what I'd like to call the dusk ages. You know, it's not quite the dark ages, but it's definitely not the age of the light quite yet. We've got some darkness still happening, so including memory cards not working, and we'll get that going. Redo the intro? Yeah. Plus, I'm sure there's people that are 10 minutes. Yeah, that are going to 8 minutes.
Oh, okay.
Yeah. All right, we'll wait 5 minutes.
That's good practice.
Yeah. Just making sure everything works. And the next challenge is to explain the entire universe in 1 hour, but how's it been here for the last couple of days? I unfortunately couldn't make it here until just now. It's been great. I saw some of the stream, and I have to say I'm very encouraged and appreciative of this conference being here and doing this. And I picture next year there being exponentially more people, and then again the next year. And so thank you guys for being here and supporting this movement, and specifically coming out for this talk. The event? Oh, okay. Oh, cool. Yeah, and he's going to join me today for the second talk. Has anybody here seen NASSIM HARAMEIN speak in person? Yeah, a few of you. And have you guys seen NASSIM's videos on YouTube and stuff like this? And how many people have no idea what I'm about to talk about? Okay. It's good to know the ratio, you know. It's usually like this when I do these talks. Rogue Valley, the 45 part. Yeah. Oh, yeah.
This is the guy for the appointment of the interview.
Hey,
This is
Jamie.
Lectures.
Nice to see you.
Can you make it at 1700?
I won't in Bol. He lives in Bol, so maybe he can.
This is,
come tomorrow as well if you want.
4 o'clock or 5 o'clock?
5 o'clock. your
5
time.
o'clock. Or tomorrow
I
morning.
think I could do 5 o'clock.
5 o'clock?
Yeah.
Okay. And that's Jamie Janover?
Yeah, Jamie Janover.
And it's in room 402 upstairs in
Okay.
the hotel. There's a studio.
Okay.
And
Yeah.
we have a tight
402.
schedule.
Okay.
Yeah, 30 minutes.
Sure. 5 o'clock.
Scheduled interview.
Yep.
Normal questions.
No worries.
Nothing to be afraid of.
No, that's awesome. Yeah, thank
Okay,
you.
great.
Yeah, thanks for doing
See you
this.
then.
Yeah.
All right.
Yeah, no problem.
Welcome to day 3 of our conference. My name is Jason Verbelli, and I'm your host. The 2013 Global Breakthrough Energy Movement proudly introduces you Mr. Jamie Janover.
All right, thanks so much. Thanks, everybody. My name's Jamie Janover. I'm very glad to be here. I'm here representing a gentleman named NASSIM HARAMEIN. He is a physicist who has an organization called the Resonance Project, based out of Hawaii. And it was about 10 years ago that I first encountered NASSIM HARAMEIN at a festival. I saw him at a festival because I'm a professional musician. And so a little bit of a disclaimer, I am not a physicist. And I'm not a mathematician. However, when I saw NASSIM HARAMEIN speak, it really flipped my paradigm upside down, and it really changed a lot for me. And so I was very curious about this guy's work. So I sought out NASSIM and saw him speak over several years, many different occasions, until eventually I saw one of his classic 13-hour presentations in one day, where he goes through his entire unified field theory, a theory about everything in the universe, and how it's all connected. And I sort of landed it. I think I figured this out enough that I'm going to try to explain it to other people because I was so interested in it. And I went to him and I said, is it okay if I try to explain this to people? I don't want to mess up your theory. And he said, well, actually, I need help. I could go around the rest of my life trying to explain the stuff that I've already figured out about the universe. What I really need to do is stay in my lab and continue to do my research and have other people go out and explain my theory to the layman. And so what I do now for the Resonance Project, and I've been doing this officially for about 5 years and unofficially for about 10 years, is I do NASSIM HARAMEIN's PowerPoint presentations for him and explain his unified field theory to groups around the world in different situations. A lot of times at festivals, also private, smaller talks. I also do weekend seminars for him called the Delegate Program, where we help to teach people to, again, explain this further to other people. And so really my job is to try to condense a vast body of information down into bite-sized digestible chunks in a relatively short amount of time. So literally what I do a lot of the time, like I have 1 hour to speak right now, and Nassim's unified field theory explains the entire universe. So the trick is to explain the entire universe in less than an hour. Now, that being said, you have to choose exactly what parts of infinity you're going to go for and then lay that out. So I will not be able to get to all the aspects of this theory. I'm going to gear it, of course, towards the theme of this conference and have to give you kind of the Reader's Digest version of the Cliff Notes version of the Reader's Digest version of this body of information. And so NASSIM HARAMEIN is doing what a lot of physicists are doing right now, which is trying to figure out how everything works and how the universe came to be. We keep thinking that we're closer and closer to coming up with one set of information, one set of understanding that describes the entire universe, no matter what you're looking at. And over a long period of time, the standard model of physics has been evolving to become more and more complete, more and more detailed. And not very long ago, we had a split, a division in the math that describes the universe. Because, of course, physicists use the language of math to describe their ideas by writing mathematical equations that describe the processes they observe in nature. And Einstein did a really good job of describing large cosmological size objects with his relativistic field equations. And then when they tried to apply the math of big things down to the quantum level and subatomic particles, it didn't work out at all. And they had to develop a whole other set of math called quantum field theory or quantum theory that is different math than Einstein's math for the large. And so ideally, what we're looking for is one set of information or one set of math that will describe everything in the universe from the infinitely large to the infinitely small. So this is what NASSIM has been looking for. It's what Einstein was looking for, and he did not achieve this before he died. And so we know that there's major problems with physics right now. In other words, we have a standard model of physics. It's being taught at the University of Colorado tomorrow morning. The kids are going to open up their textbooks, 101 style. They'll probably open up Gravitation by Wheeler, Thorndon, Meissner. They'll go through, they'll learn the standard model, the history of physics that got us to the point where we are now, where we say this is what we think is going on. Particle physics is one of the dominant theories that's going on right now. There's string theory. There's all these various theories that are kind of competing, and we're testing them, and we're making observations. And in a lot of cases, we're making observations of the universe that do not fit into the standard model. This has been happening over a long period of time, and we've had to make mathematical patches to kind of correct the model versus what we observe. And now we've got patch upon patch upon patch upon patch to the point where our theories are so incredibly complex, you practically need a degree in mathematics just to understand the theory. And as we have seen in the history of science, it turns out a lot of times that the simpler explanation turns out to be the correct one. And what you'll see here is that NASSIM HARAMEIN has actually come up with a very simple explanation, really, for the universe that's simple enough that even kids in elementary school can understand the basics of it because it's based on geometry, something that we all experience and observe in our daily life. And so what I'm going to do here is give you a very general overview of what NASSIM talks about and try to hit on the major points and try to explain how this would, of course, relate to the creation of energy. Because if you understand how the universe works and the dynamics and the structure of the universe, it should help you in your pursuit of making a piece of technology that understands how that dynamic works and gets energy directly from the universe without hopefully having to dig into the ground and essentially rape the earth of its resources to find some stuff that's been compactified over a long period of time with lots of pressure and then release it very quickly with this thing that we call combustion. As we know, combustion's not such a good idea, releasing all the particulate into the atmosphere, causing greenhouse effect, et cetera, et cetera. So NASSIM has been working hard in the last few years in his lab on a new evolution of his theory. He put out a series of papers, and his most recent paper is about quantum gravity and the holographic mass. And so he's come up with now a theory that is even more complete than he had prior. This paper just came out in January of this year, and so there's a lot of exciting new developments that I'm going to bring to you. But to give an overview of what NASSIM has been working on in his life, NASSIM is an independent researcher. He does not have a formal degree. He does not, he's not part of a major university. He doesn't get grants from the government and stuff like this. And so as many of you know, being an independent researcher and coming up with an alternative theory of everything that's not exactly in alignment with the standard model, he's been up against the tide of the establishment and the difficulty of getting your information out there through peer review channels that are largely insular and supporting the work that's already been there. When I saw NASSIM first speak, it was as if I thought I lived on a flat planet, and I saw Galileo do a presentation where he explained that we live on a sphere. And I was, what are you talking about? Some of the stuff he said just seemed so off the wall to me, but the more I looked into it, the more it resonated, and now it's to the point where I'm presenting his material for him. So we're going to try to understand the universe, and by understanding the universe, create technology that works in harmony with the universe instead of literally blowing up the universe, basically. One of the most foundational things that we know of about in physics that we teach kids in probably grade 5 or something like this in geometry class is about the dimensions. Everybody kind of assumes, oh yeah, we live in the 3rd dimension. Yeah, I saw a 3D movie. It made it look real because that's reality. That's where we are now. But what are they talking about when they talk about the dimensions? And so NASSIM will remind us about the early days of when you go to school, a geometry class. The teacher will put a dot on the blackboard and tell you that this is an infinitely small point in space. It has no width, no depth, no height, no mass, no volume, and it's actually an imaginary dimension that doesn't exist. We call this 0D, right? You could also call that a singularity. Now, right away, here we are on the absolute base level of the standard model, the foundation upon which all the rest of physics is based. Wouldn't you want to observe something that actually exists as the foundation of your model? Doesn't it bother you a little bit? The foundation of the standard model starts with something that doesn't exactly exist. NASSIM in that class, when he was age 7, said, "Excuse me, what do you mean it doesn't exist? I could see the dot on the blackboard." It's like cheeky little kid, right? He didn't do so well in school because he was questioning everything, just like Einstein, who didn't fare so well in college and barely graduated. NASSIM's like, okay, I'll bear with you. Put a bunch of these non-existent, infinitely small points together like this in a row, and you get a one-dimensional object. Again, we've never observed a one-dimensional object. This is a theoretical dimension. We've just made this up in our head to come to some sort of construct so we can evolve to the point where we can actually sink our teeth into something that actually is observable and verifiable. You could take 3 or 4 of these lines, right, and you put them together like this. You get a flat plane, 2D. Everybody knows about those. That's like flat books and paintings, flat surfaces. Of course, if you look at any flat surface with an electron microscope, you can see that it's not flat at all. There's no such thing as flat. What do you mean flat? NASSIM was once on an airplane with a famous mathematician, so he couldn't get away from him, and he said, "How thin are these 2-dimensional planes?" And the guy's answer was, "Infinitely thin." It's like, okay, great. So we're talking about a non-existent, infinitely thin flat plane in space. Have we observed these anywhere in the universe? Not really. But check this out. You take your magic wand like this. Do-do-do-do-do. I'll give you an infinite number of infinitely thin, non-existent things. You're not going to put those together and make reality out of it. Yet, this is what our model says. You take 6 planes You place them like this, now you have a cube. Oh, cool. Now you've got width, depth, height, mass, volume. That does exist. That's where we are now. That's the third dimension. Now, I explain this to people all around the world, and every time you go through this, people that aren't physicists, that aren't scientists, will kind of chuckle or like tilt their head to the side because you can tell that they think there's some shred of a chance that our model for the dimensions might not be completely correct. As a matter of fact, there's some chance that this model is absolutely, completely incorrect. If that is true, if we are incorrect about our assumption about how the dimensions work, then no wonder the string theorists are pulling their hair out right now, because string theory, as it stands right now, has an infinite number of solutions. Okay, great. So if we want to solve that, that could take, by definition, forever. And we know we don't have forever to figure out our issues on this planet right now. If we continue burning stuff and blowing things up to make energy, to make pistons move, to make wheels turn so that we can get from point A to point B faster than if we were running, we will destroy this planet in a few generations, and we will not be able to live here anymore. So we do need to figure this out. So maybe we should go back and make sure 100% that every level of this pyramid of knowledge that we've been building to get to the point where we have a unified field theory that explains everything, that the base levels are absolutely solid before you start stacking more and more cognitive weight on top of there and get to these mathematical equations that end up having holes in it because we observe things that don't fit our model. So NASSIM says, let's go back to the foundations of the standard model, for example, the dimensions, and really look at this logically. If you look at this logically, mathematically, you're taking something that doesn't exist to make something else that doesn't exist, to make something else that doesn't exist, and then you're creating reality out of it, whereas mathematically, what you're talking about here is non-existence to the fourth. Okay? Yeah, it's kind of strange. And so NASSIM's theory actually starts with him getting home from school that day in a bus, and he had a very similar kind of vision that Foster Gamble had, driving home from school in a bus. I don't know what the story is with the buses, but he zoomed out of his own perspective and looked back out on the bus, Google Earth style, and he keeps zooming out and zooming out. The bus looks like a dot, then the Earth looks like a dot, then the solar system looks like a dot, then the galaxy looks like a dot, then the universe looks like a dot. If you go far enough away in perspective from anything, it can just get reduced into your horizon as a tiny little dot. So NASSIM's theory about the dimensions is that we're 180 degrees completely backwards from correct. Third dimension doesn't exist, second dimension doesn't exist, first dimension doesn't exist. The only dimension that does exist is the dot. It's just that there's an infinite number of different sizes and scales of these dots embedded inside of each other fractally from infinitely large to infinitely small. NASSIM would say that everything in the universe is made of an infinite number of dots. So really, there's just infinite scalar dimensions of singularity, if you will. And so this could instantly confuse somebody because they've been taught, first of all, something completely different. It also brings up this strange concept of like, wait a minute, how can there be an infinite number of anything inside of something finite? And I always use my cup of coffee as an example because it's an excuse to sip coffee, which helps my presentation. So how could there be an infinite number of dots inside of this cup of coffee, right? It's not the whole entire universe. So in a simple illustration, NASSIM explains how within any finite boundary condition, you can actually divide that space into smaller sections of space to infinity. So let's take, if you want to enclose the most space you can enclose with a single line, you would use a circle. And now we're going to subdivide space inside of there. And we'll use the figure that encloses the smallest amount of space with the fewest number of lines, the triangle. So right away we have a special relationship. You could subdivide space in any way you want. NASSIM specifically chooses triangles because he's working towards the geometry of space-time that he's figured out. Let's polarize this space and put another triangle in there because everything in the universe that we observe is polarized. Now you've created a series of smaller triangles, which means you can create smaller circles. And then you can continue to subdivide in this way, smaller circles, smaller triangles, smaller circles, smaller triangles. And you can keep zooming in like this forever. You could zoom in on one of these smaller circles till it looks like the larger one, fractally, and then tell your computer to zoom in and chop it down, zoom in and chop it down, zoom in and chop it down. You could do that multiple times per second forever. As long as you have power running to your computer will continue to subdivide that space and zoom in. At no point will the universe say, stop right there, you can't go any smaller than that. So when you explain this to even a young person who doesn't have mathematical or scientific experience, they can land that information. It makes sense, right? You can go in smaller and smaller. This circle could start out the size of a galaxy or the size of a quark. It doesn't really matter. You can always get more information from your finite boundary. So inside any finite boundary is the possibility of an infinite amount of information. And then if you can get people to land that, that's great, because then you can just look at them matter-of-factly and say, you're an infinite being. And you're not saying it in a philosophical, spiritual, kind of abstract way. You're saying literally, physically, you're an infinite being because your supposed finite boundary has the possibility of containing within it an infinite amount of possibility, infinite amount of information. So NASSIM's work has aspects of it that affect the way we do science, and it affects the way people perceive themselves. And so it's been an incredible process for me personally to explain this information and see how it affects people, whether they're working on a new energy device or just trying to improve their daily life and have more fun and meditate and things like this. So this is an example that led NASSIM towards wanting to find how could I get some of this information that exists in every point in space to come out of space. If you can get information and energy to come right out of the structure of space, then you're really getting somewhere. This little animation just gives you a sense of scale. When you say, oh, infinitely large and infinitely small, it's very difficult to visualize that. Most people have a sense of how large the Earth is, and then you start to think, wow, Jupiter's pretty big. Wait a minute, Jupiter's tiny. Oh, the sun's really big. Wait a minute, the sun's tiny compared to some of these other stars. These are individual stars, you know. We have trillions of these and lots of space in between them. So it's very difficult to even conceive of how large of a scale we're talking about when you start to go to these scales. There's the size of the Earth relative to the sun. Luckily, we're not that close to the sun, but so when I start talking about this stuff and I say that NASSIM thinks that it's scalar dimensions of singularity, in other words, boundary condition inside a boundary condition inside a boundary condition, smaller and smaller and smaller and smaller to infinity, and larger and larger and larger to infinity. And each one of these things, these boundary conditions, can be considered a singularity. As soon as you say singularity, you have to explain to people what a singularity is, which is having to go into a brief review of Einstein, who talked about space-time and gravity being the result of space-time curvature, or a curvature happening as a result of gravity. So you can picture the Earth creating a gravitational field, the moon gets caught in it, it falls into the orbit of the Earth, and the singularity is the point where Einstein said theoretically space-time could curve like the surface of a trampoline. If you put a heavy ball on a trampoline, if it was an infinitely heavy ball, you could dip your trampoline infinitely down to this tiny little spot that's got such an incredibly strong gravitational field that it sucks everything into it, including the electromagnetic spectrum, which is why they call it a black hole. Light gets stuck into a circular orbit and spins down to stillness, to singularity. So NASSIM is basically saying, when he says that the universe is made of an infinite number of scalar dimensions of singularity, he is literally saying that everything in the universe is centered by a black hole. And this should make everybody who's familiar with the Standard Model go, what are you talking about? A black hole is absolutely ginormous. It's a mysteriously black funnel in the sky that you can't even see. It's like cosmological size thing. You need a whole bunch of mass to create enough vortex to get a singularity to form. You can't tell me that, you know, there's a black hole in the center of my computer or in the center of me or in the center of anything else, but that's exactly what NASSIM is saying. NASSIM actually redefines in his physics what a black hole is. He calls it a black/white hole, spelled W-H-O-L-E, because black holes do not just absorb information and then the information disappears and goes into some other dimension we don't know. The information comes back out again. There's an equal and opposite thing that happens. The information that falls into a black hole comes back out in the same amount, and we're going to get into how that works. But you have to kind of undo this picture that I had in my head when I finished school, because, you know, I got this picture, oh yeah, black hole's like a funnel and then there's this dot there, and that's kind of the view of a black hole. But NASSIM shows that the black hole dynamic is actually something where space-time curls to singularity like this, like water going down the drain. It doesn't just curve, it actually curls. And then there's an equal and opposite curl going the other way, spinning the opposite direction, giving you a toroidal dynamic that I'm sure many of you are familiar with. And he says that this toroidal dynamic centers everything in the universe. The structure of the universe itself, the entire universe, galaxies, stars, planets, humans, cells, atoms. It's scalar dynamics of the same pattern of toroidal energy field, with singularity centering every single thing in the universe. So this is what he came up with when he added torque and Coriolis forces to Einstein's field equations. Einstein didn't properly account for spin in his equations. They were already the most complex equations ever written on the planet at the time. Wheeler, Thorne, and Meissner did work on this. Kerr and Newman added torque and Coriolis forces to Einstein's field equations, but they didn't fully properly account for the effects of spin. In other words, they attached the person observing the spin to the spinning metric and then counted the revolutions and said, oh, see, we're accounting for spin. But if you're standing still and something's spinning at the speed of light right next to you, that might affect you. You're not attached to the spinning metric spinning at the speed of light. When you deal with the non-linear effects of torque and Coriolis forces and you add it to Einstein's field equations, then instead of theorizing that space-time curves to singularity like this, like a funnel, then you get this curling aspect to the space-time manifold, curling to singularity in one direction and then an equal and opposite in the other direction, and it forms this double torus or double tube torus. So NASSIM knew that he had to look at other aspects of the standard model that he thought might have some holes in it. And so he's looking at the nature of the entire universe, the big picture. It's like NASSIM is good at pulling out perspective-wise and looking back and seeing the big picture. In other words, taking away the box, since we know there's no boxes in the universe. And when you do that and you ask the question, if you wanted to find something that connects all things, what would it be? Some people would say God, some people would say love, some people might say light or energy, but literally, physically, the thing that connects everything in the universe is this thing that we call space. Space is obviously in every object in the universe. When you look at atoms, you know, all of the matter in this room and our bodies are made of atoms. They're made of 99.999999% space. And only a very small fraction of the atomic world, 0.000001%, is this stuff that we call stuff, protons, neutrons, and electrons, which aren't exactly solid either. So the stuff that we call matter is actually vastly made of space. So if you want to come up with a unified field theory that describes the entire universe, you'd probably want to pay at least a little bit of attention to the 99.999999% part. And so far in physics, we've done a very good job and spent most of our attention looking at the 0.00001% part. In other words, we have incredibly powerful telescopes that are observing the universe. We're collecting light. We're looking at data on heat and sound and X-rays and gamma rays and microwaves and all these frequencies of the electromagnetic spectrum, which is great. But the only way that we can make those measurements is that there's stuff out there to measure. If there was no matter in the universe, there'd be nothing for light to bounce off of so it could hit our eye or hit our telescope. If there were no nebula and stars and galaxies in the universe to observe, there'd be nothing to radiate X-ray information, and X-rays and cosmic rays in this electromagnetic spectrum. So NASSIM knew that when he's coming up with a unified field theory, he needs to concentrate mostly on the nature of space. Is space just random? Is there a structure to the space? Is there a dynamic to the space? This was the line of inquiry that NASSIM was going for. And this has been known for a long time, that space is not actually empty. I think the average person, especially non-physicists, people that are thinking about energy devices and things like this, think of empty space as empty. Like, let's say we're floating in the vacuum of space, right? We're not in the atmosphere. If you move your hand like this, you're like, see, there's nothing there. There's no molecules, there's no air. If you put your hands in water, you know it's even denser than the air. If a tornado comes, it's going to take this tent right off of us. So we know we're living in a density here, but what about space? If you're floating in the density of space, is there a viscosity to that? Is there anything there? This question was asked by Casimir in 1947. He said, man, we should try to figure out if there's an energy density to the space itself. if we could isolate a little sliver of the space and get rid of all the frequencies of the electromagnetic spectrum, maybe we could find out if there's an actual energy density to the fabric of the vacuum itself. So when you say space to somebody, this word is actually representing a concept that's had many different names over a long period of time. They used to call it the plenum and the ether before Einstein came along. Then they started calling it the vacuum, space, the zero-point field, the source field, right? The quantum foam in quantum field theory. All these various names are referring basically to the same thing, that we are all made of and bathing in what turns out to be an infinitely dense superfluid medium that we call space. In other words, space is completely full with vibration. Max Planck in 1894 was the first person to look very closely at the structure of the vacuum itself and realized that space-time is not totally smooth when you get down to the quantum level, that it actually has a lot of energy to it. It's frothing, it's bubbling, it's forming little packets of energy. And that's where we got down to realizing that you can actually get down to a fundamental dividing point of the universe, a spherical volume of energy that is a discrete information packet. You can kind of think of it as the pixel size of our existence. If our reality is actually a hologram, which is where NASSIM is going with this, this would be the pixel size of the hologram that we live in. It's called the Planck's distance, or the Planck's mass. And this was worked on a long time ago, and it didn't get furthered until people like Casimir in 1947, and then later on at Seattle University in 1990, they were able to get a ball and a plate so close together inside a vacuum chamber that it was only a micron apart, and there was no way for long frequencies of the electromagnetic spectrum to get between the ball and the plate. And they measured a differential between the plates, showing you that there's an incredibly strong field of energy that exists in the fabric of space itself. So we started to develop a long time ago this idea of a quantized vacuum, a way of describing the vacuum in discrete quantized packets of energy. So NASSIM is using this Planck's distance unit for his equations to look at the nature of space and measure the energy density of the space itself. It's filled with interconnected discrete packets of energy and waveforms, little balls connected by springs, if you will. It's a way to visualize this. So the vacuum itself is quantized. If you have a quantized vacuum, that means you can start to develop equations that are going to describe how the universe works in its most foundational state at the level of the smallest possible observational unit. The Planck's distance is the smallest possible measurable distance in math and science. As soon as NASSIM said that the first time I saw him, I was like, what are you talking about? The smallest possible measurable distance? 1.616 times 10 to the negative 33 centimeters, 32 zeros, and then 1616 centimeters. Why don't you just make it 10 to the negative 6, 66 centimeters? Call that the shortest possible distance. NASSIM described, well, if you want to be able to measure the distance or the size of something, you have to be able to see it. I was like, okay, that makes sense. Well, how are you seeing things? The only way you could see something is photons of light hit an object and they bounce off of it and hit your eye. So if I was to shrink this screen smaller and smaller, photons of light could come out of a projector, hit the screen, bounce off, and hit your eye. I could shrink my screen down to the size of a single photon of light, and you would be able to see it. Remarkably, you could put a human being in a perfectly black environment, introduce one single photon of light, and your eye can detect it, which is unbelievable. But if you make the screen smaller than a photon of light, you cannot see it. And so therefore, you can't measure it. And so the Planck's distance is the width of the smallest possible photon of the frequency of light. It's again like the little pixel size of our universe. And so NASSIM is using this little discrete packet of information to describe the nature of the vacuum. So when you start to sum up all the oscillations that they were observing in the frothing vacuum, the quantum foam, the plenum, the ether, the space, the vacuum, God, whatever you want to call it, the vacuum yielded in their mathematics an infinite amount of oscillations, an infinite amount of energy in every point. And when the standard model guys got a hold of this and they took the numbers that represent how dense the vacuum is and they put it into their equations, they had a big issue, because then every equation that they ran came out to the same answer, infinity. And then they're like, great, what are we going to do? Call a press conference with CNN and have Wolf Blitzer up there? So I hear you figured out the universe, physicist. Yes, it turns out the universe is infinite. And then he's like, thanks, Lao Tzu. I thought we were doing physics. You sound like a mystic, right? Physicists don't want to sound like mystics. They need finite numbers, right? We got to deal with, something that's calculatable, not just talk about how everything's infinite. But if you dig deep into Wheeler, Thorne, and Meissner's gravitation, which is kind of like the Bible of Einstein's field equations, tucked way in there, it was hard to find this for NASSIM, when he eventually found this quote that shows that what they did is they just said, don't worry about that infinite density of the fabric of the vacuum. We're just going to sweep it under the rug. If you do an equation and you get a result, a number that's an infinitely small number, maybe you could sweep it under the rug. But if you get an equation that gives you an infinitely large number, you can't just sweep that under the rug and pretend it's not important. This quote shows this is exactly what they did. Present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formally be, notice this word, infinite, if not removed by this fancy word that we just made up. In other words, this has been such a pain in our neck that we're just going to introduce a constant mathematically and neutralize the effect of the infinite density of the fabric of the vacuum, and then proceed about our business as if it wasn't important. And so even to figure out how they got to the density of the fabric of the vacuum, they had to use the Planck's distance as the little packet of energy and say how many of these little Planck's distance units can fit in, say, a cubic centimeter. Then we can get a measurement of the density of the energy that exists in a cubic centimeter of space. So Planck is giving you what are natural units. They're the only units of measurement that are free of any arbitrary concepts and are based on fundamental physical constants. In other words, this is a fundamental division point of the structure of the vacuum. Is that to say that there's nothing that exists smaller than the Planck's distance? No. That's to say, from our perspective, from our scale, using our sensory apparatus and all the technology available to us, at this time, we do not have a way of accessing information that's smaller than the Planck's distance. And on the other end, right now, according to our greatest theory called the Big Bang, the universe has been expanding since the Big Bang happened. It's accelerating faster and faster. They just upgraded the age of the universe from 13.75 to 13.8 billion years old because they observed a galaxy slightly farther away than we've observed before. But that's kind of our outside boundary of the scale of the universe. Right now we don't know how to measure anything outside of our universe that's a boundary condition, and we don't know how to measure anything smaller than the Planck's distance. That's the range of our observations in the world of physics right now. So that's what we can talk about. And so when you start thinking about the level of scale, it's just mind-boggling. The scale slide that we saw from the Earth to the largest sun or largest star in our galaxy pales in comparison to when you're looking at something as small as the Planck's distance as compared to even something as large as a proton. The Planck's distance is incredibly small. You can fit an enormous number of Planck's distance units inside of a proton. And that's what NASSIM started to do. He started to look at the structure of the vacuum. If he's got a quantized vacuum with a tiny little increment that's a little pixel, he started to calculate how many of these would fit inside of various sized objects. And he very famously starts out with the size of the proton. He has a paper called the Schwarzschild proton where he solves Einstein's field equations and shows that the proton itself is actually a miniature black hole. And that paper is available on NASSIM's website, resonance.is, as well as all of his other papers. But his most recent paper, talking about quantum gravity and holographic mass, he says if you took the Planck sphere, because this is the other issue, right? When they were measuring the density of the fabric of the vacuum, they were using cubic units. Do you see the nature and the universe making cubes anywhere? No. And so if you're going to start pixelizing and quantizing the vacuum, you might want to think of them as spherical units. Because if you said to a physicist today, what's the one thing the universe is doing right now? You can only tell me one thing. They might have to say, the universe is making spheres. Various spheres of different sizes that are all spinning. Nothing but spinning spheres. All of our atoms are spinning at the speed of light. Protons spinning around in the nuclei of all the atoms. The Earth is a sphere, obviously the solar system, galaxies, etc., etc. So he says, take this example. Take a proton, and you've got Planck's distance, little spherical packets of energy inside the proton. There's 10 to the 60 Planck's distance spheres inside of a proton. A 1 with 60 zeros after it. So now let's take each spherical Planck unit and make it the size of a grain of sand. Okay, so now we've got 10 to the 60 grains of sand. If you took the proton and you made each little spherical packet of energy in there the size of a grain of sand, then the proton would be the size of from here to the next closest star, Alpha Centauri. That's how big the proton would be if you were to, make it as big in scale as if there's grains of sand for every proton, for every Planck's distance sphere. So we're talking about an incredible number of Planck's distance spherical units inside of something as small as the proton. And so again, it's like looking at these various scales. Then you start to realize that the universe has a lot more complexity in terms of its scale than we had imagined before. Because even just dealing with the proton itself was kind of at the limits of our ability. Now we're able to make circuits that are dealing with individual atoms and things. And so the key here is to look at how these spherical packets of energy are organizing themselves. Because space is the one thing that connects everything. That means that there's a specific geometry to the structure of the vacuum. So he looks at this renormalized vacuum density. This is the number that they swept under the rug with a mathematical constant, 10 to the 93 grams per cubic centimeter. A 1 with 93 zeros after it, grams inside of a cubic centimeter. I mean, you could shrink this hotel to be a cubic centimeter, and you can imagine how much density that would be. Let's just shrink the Earth. Imagine making the Earth a cubic centimeter. Let's just cut to the chase, shall we? Shrink the entire universe into a cubic centimeter. All the stars, all the galaxies, all the comets, all the gases. They estimate that the weight of all the regular mass of the universe would weigh 10 to the 55th grams. And now NASSIM is here telling you that inside of a cubic centimeter of vacuum, there's the equivalent energy density vacuum fluctuations that are 39 orders of magnitude denser than if you squash the entire universe into a cubic centimeter. And so this should make people a little bit baffled, because again, like, what do you mean? I can move there's no density there. How is that possible? That's got to be the biggest anomaly in the history of physics. You're telling me that the vacuum is completely full, but I completely say it's totally empty according to all my calculations? That's got to be an incredibly difficult anomaly to try to, overcome in the standard model. So if you look to see how they overcome it, they didn't. That's where the sweeping under the rug renormalization comes in. And so for NASSIM, I'd say that he thinks that this possibly renormalization as a concept in itself is probably the biggest mistake in the history of physics, because from there, everything gets thrown off, and you start to think of things in a very different way. So they've figured out now, we know for sure that there is this energy fluctuations in the structure of space-time itself. We've even gotten to the point where we've been able to get real photons of light to come directly out of the fabric of the vacuum. It's a dynamical Casimir effect. And so NASSIM looks at this and he realizes now we should be able to really get into understanding how space-time works if we start to be able to quantize it and express it mathematically. And so that's what he does. He looks back at gravitation, Wheeler, Thorne, and Meissner. There's this classic story. I was fortunate enough to go on a tour of Australia with Foster Gamble last year called the Solution Summit, where this incredible promoter in Australia got a whole bunch of solutions-based people, Foster being one of the greatest of all of them. And I was there to help describe NASSIM's work. And it was about 20 years ago that NASSIM was giving his last presentation ever because he was so frustrated he wasn't getting anywhere. People were ridiculing him, laughing at him, dismissing what he was saying. he got up there and started describing the geometry of the structure of the vacuum, and Foster Gamble was like, good job, kid. You're on to something. He was probably like 23 years old or something like this. Foster Gamble gave NASSIM $800 a month, his first per diem, his first grant to do his research. And then, of course, Foster went on to make Thrive, put NASSIM in the movie, in the introduction to Thrive, and describes the structure of the vacuum and the dynamics of the torus and stuff like this. But Foster Gamble, picture this. Foster Gamble brings NASSIM HARAMEIN with his ponytail and his funny accent and his no PhD in physics to Georgia Tech, to a conference that includes Paul Serac, the guy who started string theory, sitting there, you know, round table discussion style. And NASSIM starts flipping through gravitation because he wants to understand the standard model and get to the point where you're, you know, talking about what's happening. And you get to page 719 and you get this picture that we show to all the college students about the nature of the beginning of the universe, which started with a singularity, an infinitely small point in space. It blew up in a giant explosion. Somebody sarcastically called it the Big Bang, highly technical term. And then the name stuck. So that's our most advanced solution for the universe, this Big Bang. They love doing that stuff, right? When they found the little particles that hold everything together, what do they call them? Gluons, right? And when they realized, wait, according to our calculations, there should be a certain amount of mass in the universe, and they looked for it and they couldn't find it, instead of saying, uh-oh, we might have made a mistake, they did something that drives NASSIM insane, called physics as you go. Oh, if we invent a new type of matter and then throw it into our theory, it all works out perfectly. But we can't find it. We can't see it. What should we call it? How about dark matter? Because it's so dark we can't see it. NASSIM's just like, you guys have got to be kidding me. Really? You just invented a new type of matter and threw it in there? Same thing with when we found the nuclei of all the atoms, right? You take two positively charged magnets, try to put them together. It's not happening. Coulomb force is forcing those apart, right? Protons are all positively charged. Neutrons have no charge. So the nuclei of all the atoms, why is that all being held together? It should be pulled apart by the Coulomb force. It's got to be an awfully strong force holding all that stuff together. We have no idea where that comes from, but it's really strong, so we'll just make up a new force. Oh yeah, we'll make up a new force. What should we call it? How about the strong force, because it's so strong? It's like, really? I was sitting at NASSIM's house one day. We go to Wikipedia. We look up the strong force. They don't tell you where it comes from. They don't know where it comes from. And then they were like, uh-oh, we just discovered that protons have 3 quarks in every proton. And so that's an exponential more Coulomb force that we've got to overcome. Uh-oh, now there's got to be an even stronger force holding that together. How about the strong force? No. Oh, we'll get artistic. We'll call it the color force, right? You look up the color force in Wikipedia, in its description, it's an infinitely strong force. Oh, really? Great. You're just going to throw in there into the standard model. Oh, yeah, by the way, there's an infinitely strong force called the color force. What? Where does that come from? Where's the source of that? Where's the source of spin? Where's the source of charge? Standard model doesn't actually have very much of this stuff figured out. NASSIM knew he needed to go to the root of these problems. So he's looking at these guys, and he's like, yeah, I like your little model of the guy blowing up the universe like a balloon with the galaxies that are pennies glued to the balloon. As the universe expands, the galaxies move apart from each other. You know? And I asked NASSIM, so if the galaxies are moving apart, that means the galaxies have to be expanding, which means the solar system is expanding, which means the Earth is expanding, which means a meter is not just a meter. As the universe is expanding, a meter is getting a little bit longer every day, right, NASSIM? He said, oh no. According to the standard model, you ready for this? The universe is expanding down to galactic size, but everything smaller than galactic size is not expanding. Right, exactly. And so even people without a PhD in physics can be like, that's a little strange. I thought they were very logical in the standard model. And so NASSIM says, what I really want to know is, who's this guy? Can you imagine Paul Serac being like, Foster, you're bringing this guy, he's going to talk about God in the physics department? Wait a minute. It wasn't until the Tao of physics that somebody like Fritjof Capra took a good look at ancient mysticism and Taoism and matched it up with Einstein and said, Lao Tzu and Einstein are saying the same thing. They're just saying it from different perspectives. And I was like, oh, this makes sense to me. I read Tao of Physics about 25 years ago. That was my first book that sent me on this whole journey of reading all the books for the layman about physics, Brief History of Time, Stephen Hawking, right, Elegant Universe, Brian Greene, Dancing Woolly Masters, books on chaos theory, books on string theory. So by the time I saw NASSIM, I was like, yep, okay, that makes sense. What? What are you saying? I don't know about that. And then I looked into it, I was like, oh, now I see what you're talking about. He's not talking about God. Can you imagine NASSIM saying to Paul Serac, for every action, there's an equal and opposite reaction? Right, like every single person knows about this, because that is the one most known, most tested, most proven thing in the history of physics, that no matter what you're doing, no matter what observation you're making, you know there has to be something equal and opposite to that happening at the same time. So it would make sense that if your guy's blowing up the universe balloon, his lungs have to contract. So have you heard about the big contraction? In other words, the standard model is doing a fairly good job at describing half of what's going on. If the universe is accelerating in its expansion, there's got to be a hell of a thing contracting to cause that expansion. And so, cutting to the chase, basically that contraction is the vacuum itself, the structure of space-time, collapsing in on itself at all scales to singularity, forming scalar dynamics of black holes. So NASSIM would say that we live inside of a black hole right now. It's called the universe. A black hole is going to look very different depending on where you are in relation to the event horizon, that threshold beyond which you get sucked into singularity. If you're on the inside of the event horizon of a black hole, it might look black, like the sky at night. Isn't that bizarre? There's trillions of galaxies with trillions of stars in every galaxy. Why isn't the sky completely white with light? The short answer is light cannot escape our universe. If you shine a laser into space, it's eventually going to get too close to a gravitational field like a star, slightly bend the light, then it gets bent again, it gets bent again. Eventually the light will curve right back into the universe. If you do the calculations, the universe obeys what's known as the Schwarzschild condition. Schwarzschild being the first guy to solve Einstein's field equations in a foxhole in World War I, ducking bullets. Oh yeah, I could solve this. Mails it back to Einstein. Whoa, he publishes it 2 weeks later, and then unfortunately Schwarzschild got killed in the war and never could work with Einstein again. But so NASSIM goes on to describe the nature of black holes. I'm going to have to go pretty quickly because I want to get to some stuff, and as you can tell, it's hard to describe the whole universe. I have 15 minutes left to get through the rest of the universe. But this is an important graph, because even the detractors that go after NASSIM, because back in the day, if you dared to say the Earth wasn't flat and we weren't the center of the universe, you actually might get burnt at the stake. Like Galileo didn't get it formally excused by the Vatican until 1993. You know what I'm talking about? And so to today's world, if you start talking about this kind of thing, somebody might make a blog about you and like badmouth you and give you bad reviews on Wikipedia and stuff like this, but they never go after this because this is so incredibly testable and the data is out there. This is a simple graph, X and Y axis, measuring the frequency versus the radius of all these various spherical objects that you can observe in the universe. Starting here down in the lower right with the largest thing that we know of, the universe, with a very low level of background vibration. And then you've got a data point that's for the average large galaxy, then the average small galaxy. The S is solar size, A is the atomic size, and then way up there in the upper left corner is the Planck's distance, 10 to the negative 33 centimeters, incredibly high vibration. And so just by measuring these things, you quickly see that there's a direct linear relationship between the frequency and the radius of all the objects in the entire universe. This graph right here by itself basically proves there has to be structure in the universe. In other words, it's not just a bunch of random particles floating about willy-nilly, and we're lucky that they self-organized in the primordial soup with a lightning bolt to create DNA and RNA, and now here we are, 100 trillion cells, all perfectly talking to each other. All we have to do is eat, sleep, drink, and dream, and our body does the rest. No problem. They call that the unconscious mind, by the way, that does that. Consciousness is, why didn't she call me back? Do I look okay? What's going on? Seems like we've got everything backwards. Consciousness is the fact that biology is doing its thing just fine. All we have to do is eat, drink, and sleep, and dream, and everything else happens. So the interesting thing here is if you plot the mitochondria in a cell, the vibration of the mitochondria versus the radius of the cell, it obviously is bigger than an atom and smaller than a star. It actually bisects the scale. In other words, NASSIM would say that the biological scale, the scale that we're on, is about halfway between the biggest thing we can measure and the smallest thing we can measure. I think most people think of themselves as tiny compared to the universe, but you're as different in scale from the Planck's distance as you are from the universe. We're actually ginormous, huge in scale compared to something like the Planck's distance, where you can put 10 to the 60 of these things inside of a proton, and there's something like 100 trillion atoms in every one of your 100 trillion cells that make up your body. So it's no small feat that we're maintaining the organization that we're measuring. So he's saying that black holes on all scales obey this same linear relationship of frequency versus radius. Therefore, there has to be structure in the universe. The next question is, what is the structure of the universe? And then what is the study of structure of space? It's called geometry. And so he starts to look at the geometry of the fabric of the vacuum. Now, this is where the proton, Schwarzschild proton paper comes into play. He takes this tiny little Planck's distance unit, and he looks at the energy density of the fabric of the vacuum, 10 to the 93 grams per cubic centimeter, and then he says, well, how much of that energy is available inside of a spherical proton volume? Because protons have a volume too. At the rate of 10 to the 93 grams per cubic centimeter, if you look at how many vacuum fluctuations exist inside of a proton, the answer comes out to, remarkably, 10 to the 55th grams, the mass of the universe. So NASSIM is saying, literally, that a proton has the equivalent energy density vacuum fluctuations of the regular mass of the entire universe. And so one way of thinking about this and expressing this is that every proton in the universe is feeling the cumulative weight of all the rest of the protons of the entire universe pushing down onto it. That it's actually a hologram. It's a hollow fractal graphic theory. That it's actually, you can kind of think of it as one proton that's subdividing itself smaller and smaller, organizing itself in this way. And so this will start to make people go crazy, and they'll say, wait a minute, you're saying a proton weighs 100 trillion tons or something like this? You're insane. You're totally off. You're off by 38 or 39 orders of magnitude. This is ridiculous. But yet, if you start looking at another one of these scaling laws of mass versus radius, these again are all black holes. Here's NASSIM's Schwarzschild proton, falls right near the line. And then down here, there's the standard proton. That's the standard model's description of what a proton is. Which one do you think is correct? Again, people don't go after this. I have a feeling it's going to turn out and to be accepted, hopefully, in a short time, that we know that the proton is actually a black hole. If we understand that, then we should be able to recreate this dynamic with a bit of technology. So really quickly, I want to be able to get to the geometry of space-time. What? Chichen Itza? Wait, where did that come from? That's because around the time NASSIM was trying to figure out the geometry of the fabric of the vacuum, he was sick of teaching skiing all year long, British Columbia, Australia, British Columbia, Australia. He went to Mexico, and he thought, whoever built this knew some serious geometry. And I'm trying to figure out the geometry of the fabric of the vacuum, a geometry that would explain how it's possible that space is completely full, but we perceive it as completely empty. It would have to be a geometry that is perfect in every possible way, equal and opposite in every possible way that you could look at it in 3 dimensions. A structure that has symmetry, that can scale infinitely bigger and infinitely smaller. So he thought, maybe I should look into the architecture of ancient civilizations, because they knew some serious geometry to be able to build this so that at 5:41 p.m. on the equinox, as the sun is setting, the light from the sun casts a shadow on the staircase to make it look like a serpent. You have to know how to set this up from stone one to do this. You have to know some serious geometry, and it was built a long time ago. So NASSIM said, well, maybe I'll look into this. And he found a book about the secret of the Mexican pyramids, where when they talk about Teotihuacan here in Mexico, in the end, the Mexicans were trying to tell us that there's an important relationship between a sphere and a tetrahedron. And if you put a tetrahedron perfectly inside of a sphere, one of your tips hits the pole, and the other 3 intersect the sphere exactly at 19.47 degrees latitude. And if you put a tetrahedron inside of the Earth, the big island of Hawaii is right at 19.47. Right at 19.47, there are these 2 bays on the big island, these 2 inlets, and that's where all the whales and dolphins go to give birth. It's also exactly where the city of Teotihuacan is in Mexico at 19.47. So not only are they expressing it through their monuments, they're expressing it by putting the city on that same latitude on the surface of the sphere that we're on. we see this not just on our sphere, but in spheres around the universe. The big red spot on Jupiter is at 19.47. It's been there since we started observing it 350 years ago. There's increased sunspot activity on the sun at 19.47 in either latitude, because of course you could put a tetrahedron facing either way, getting a star tetrahedron. You've heard about the Bermuda Triangle and maybe the Devil's Triangle. Well, there's triangles all across the world that have these strange anomalies called the vile vortices. Hugh Newman does some great work on this stuff. Megalithomania is his website. And so when NASSIM started looking into tetrahedrons, of course, it didn't take him long to find Buckminster Fuller's work. And Buckminster Fuller came up with this idea of the isotropic vector matrix, which is a tetrahedron made of 20 smaller tetrahedrons. This is highly structured. It looks very equal and opposite. Maybe this is on its way to being the structure of the vacuum. But wait a minute. NASSIM was able to figure this out in his head before he had a laptop computer, because he was doing this 20 years ago, before the first IBM laptop came out. He was living in his van. NASSIM did a lot of his research as a younger man on a very, very small budget with no lab, and was visualizing this in his head. And he realized, wait, there are these cavities in there. There's no equal and opposite to that. So maybe we need two of these things, as above, so below. But that's not really forming an equilibrium either. When you push them together, though, then you start to get to some serious symmetry. And this geometry in the inside is formed, the cube octahedron, which is what Buckminster Fuller calls, the vector equilibrium. It's 8 tetrahedrons pointing into a single point, giving you 12 radial vectors. Each of the radial vectors are exactly the same length as all the edges. It's the only three-dimensional geometry that's in perfect vector equilibrium. And so this is the type of geometry that would describe how it's possible that the structure of the vacuum is infinitely dense, but we perceive it as completely empty. It's forming a vector equilibrium on all scales. This slide has gotten a little bit messed up by the aspect ratio, but the 3D vector equilibrium is something that forms inside of a star tetrahedron made of 40 tetrahedrons. But what about these outside tetrahedrons? Those are not encapsulated. We need to get to a scalar geometry that's a fractal. So if you start stacking more tetrahedrons on the outside of the 40 you already have, when you get to a total of 64 tetrahedrons, then you get a vector equilibrium, a cube octahedron, inside of a cube octahedron. That's supposed to line up a little bit more. It's a little off. But it's the beginning of an infinite fractal division of space-time. In other words, the fabric of the vacuum is an infinite tetrahedral array, and it forms octaves of perfectly balanced geometry. So no matter where a force comes from, there's an equal and opposite structure in the space itself counterbalancing that force, and you get what we call space. There's nothing there, but it's actually infinitely full with energy. It's just sitting in such a perfectly balanced state that all forces are canceled out. And so you can kind of think of space as, I like to think of it as a tapestry, a fabric of singularity, where space-time is curling to stillness at every point, forming this infinitely dense superfluid medium from which everything arises. All energy, all frequency, all vibration, all geometry comes right out of the structure of the vacuum itself. And so now what NASSIM is working on in his lab, which I'm sure many of you are as well, is creating a device that mimics the dynamics and the structure of the vacuum so that you can get energy to come right out of the structure of space. If you can pull 1/1,000,000th of 1% of an infinite amount of energy out of the vacuum, you have an infinite amount of energy. Because 1/1,000,000th of infinity is infinity. That slide, by the way, got totally messed up by the... here's another view of the 64 tetrahedron grid. You can see the building of it. You get to 512 tetrahedrons, you get to another octave. 1,024 tetrahedrons, another octave. The computer programmers are like, oh yeah, computer programming, memory works like this, the DNA molecule works like this. And then it turns out the I Ching works like this, the Mayan calendar works like this, and quickly NASSIM takes this information into ancient cultures. It's a very interesting aspect that I do not have time to talk about. I have 5 minutes left. I wanted to maybe take a question or two, but I wanted to show people at least this important animation. We always teach kids that the planets circle around the sun, but we forget about the fact that the sun is moving quite rapidly. And so the planets are actually making a phi spiral through space as we move. And even in this room, you can tell people are like, we can make the movie Avatar, but we can't make a proper animation to show kids, oh yeah, here's the dynamics of your local environment. In other words, this is not accurate, right? The sun is moving in a spiral, right? And the planets are not like they're at a 60-degree angle to the motion of the sun. But in any case, pretty soon we're going to have a dynamic here that shows that everything is a spiral, including all energy, all frequency. Light from the sun is coming at us in a spiral. It's all spiral dynamics within the structure of space-time. So if you understand the infinite structure of the toroidal field that we live in, toroidal dynamics inside of an infinite tetrahedral array, then you start to really understand the structure of everything. And so NASSIM is trying to make a device that will imitate this field, in other words, create a singularity, a contained black hole in a can, as he likes to call it. We weren't able to talk about this until just recently. If you want to look on the US patent website, you can look up NASSIM HARAMEIN. There's a patent for his device. It took him 4 years to the day and $150,000 in lawyer fees, but he got a patent for a device that he labeled would simulate galactic dynamics. Of course, if you put out a patent and you say, oh yeah, I'm going to make a black hole, you get a knock on the door from the guys with the black van outside. So I'm excited to be able to present this in this context in an environment where there's a bunch of other people working on this same stuff. And I encourage you all to go deeper into NASSIM HARAMEIN's work. You can go to his website, resonance.is. They've got a Facebook page. They've got some videos. And NASSIM has started Hawaii Institute for Unified Physics. He's working with a bunch of other physicists, including Dr. Hyson, Dr. Rauscher, and others. And so I'd like to take a couple of questions before we have to stop. Go ahead.
Yeah, is it true that Stephen Hawking, a couple years ago, this is 2010, he actually confessed that he's been wrong about black holes?
Stephen Hawking famously was saying for a very long time that black holes only absorbed information. NASSIM then came out with his paper, The Origin of Spin, a consideration of torque and Coriolis forces in Einstein's field equations and grand unification theory. And not very long after that, Hawking made an announcement. Actually, I think I was wrong about that. I think black holes do radiate coherent information, which then eventually became labeled Hawking radiation. And so hopefully we're on our way to one more question. Yeah.
I was just going to say, give a shout out to his co-author on all those papers, Mr. Rauscher.
Yeah, that's what I said. Dr. Hyson and Dr. Rauscher, he works with as well. One more? Go ahead.
Yeah, you described how
Wait for the microphone so the stream people can hear it.
You described how space appears empty because of the equal and opposite forces creating a balance. So that made me wonder if zero-point energy is coming from that field. Somehow we're either in resonance with that or perturbing that.
Yeah.
So what happens to the balance? And perhaps is that where the toroidal
Right.
energy sort of flow comes from?
Well, what you can think of is, in our atmosphere, for example, if one air mass and another air mass come together and they're only slightly different densities, one is 3 degrees warmer than the other, what happens? Massive hurricane with an incredible amount of energy comes out of a very small change in density. When you look at the cosmological level at the density of the vacuum, and then you look at the density of the vacuum at the quantum level, there's 122 orders of magnitude difference. And this is such a problem in physics that they named it the vacuum catastrophe. It's a catastrophe because the physicists are super clueless as to how it's possible that there can be such a gradient in the density. And NASSIM would describe anywhere you get a change in density in this gradient of space, you get a spiral dynamic forming a double tube torus, whether it be a galaxy, a star, a planet. So NASSIM would very much say that there's a black hole in the center of the Earth, creating more atoms, that the Earth is gradually expanding. Check out the expanding Earth hypothesis. It works for all the moons and all the planets in our solar system. If you shrink all of them, they perfectly fit together like a jigsaw puzzle. The proton is a black hole, and then very importantly, the last thing I'll leave you with is we have a black hole in the center of us. And if you sit like this, you put your body into the shape of the structure of the vacuum, into a tetrahedron, and if you act like a black hole and you have information cross your event horizon in one direction and then go the other way, something like, then you're acting in the dynamics and the structure of the vacuum, and that would maybe explain why meditation and breathing has such a profound effect on our consciousness. So thank you guys so much. My name is Jamie Janover. And thank you. And I'd like to say thank you to this conference and the Breakthrough Energy Movement for having us. It's an honor to be here, and it's an honor, and thank you to the Resonance Project and NASSIM HARAMEIN. I'll be speaking later today at 1:15 on the role of art and music and festivals and things like this on science and technology. I'll be joined by my friend Andrew Jones, otherwise known as Android Jones. He's got a bunch of his art out here, and he's going to be showing some of his art. And then we are presenting tonight at an event that I'm producing in Denver called Sonic Blossom. It's an electronic music event with Random Rab and Kalia Scintilla from Australia and a bunch of DJs. And Andrew and I will be doing that same presentation at 8 o'clock tonight at Cervantes in Denver. So come check it out. I produce a festival called Sonic Bloom, and we have a bunch of workshops on this kind of stuff. I'm eager to talk to a bunch of you and check out some of these other talks today. And I'll see you later. Thank you.
Best lecture ever. I mean,
Really?
I'm
You're the man.
I want to ask you something. Do you believe in the law of conservation of energy as a universal, absolute, certainty thing?
I mean, I guess I do.
But it seems to me